Good morning, Internet. I am Matt Booyak, and welcome to my third video on big integers in C and C++. So you may recall in the first two videos that I did on this topic, we wrote a basic big integer class and implemented multiplication and division of big integers by small integers. And the motivation for that was this problem here, problem number 20 from the Project Euler problem archive. Now, since that video, or those videos rather, we've solved a number of other problems, making our way down to problem number 25 here. And this problem asks a question involving large Fibonacci numbers. And so in order to calculate those numbers, we're going to need big integer addition. And that will be the subject of this video. So let's get into it. Let's open our notes file. Now you may recall when we did our previous work on division and multiplication, we took inspiration from the common grade school algorithm that you may have learned when you were younger. And we're going to take a similar approach for addition. So let's just take a quick look at a simple example. Let's suppose we were adding 12,345 and 7. I hope that most of you, would be able to solve this arithmetic here. And so let's just go through it. We'll start by adding 5 and 7. We get 12. Carry the 1. Add 1 and 4. Get 5. And then we can just, since we have no more carry digit, we can just bring down the remaining digits to get our answer. Pretty simple, pretty straightforward. So let's look at a slightly more involved question. Again, 12,345. Now we're going to add 678. And so the only difference here is that when adding subsequent digits with our carry, there's going to be more than one digit potentially that we're adding. Okay, so let's work through this. Start by adding the 5 and 8, and we get 13. So we'll carry the 1. Add 1, 4, and 7, and get 12. Carry the 1. Add 1, 3, and 6. That will give us 10. Again, carry the 1. Add 1 and 2 to get 3. And bring down the 1 to give us our answer. So hopefully that was all pretty simple for you. But let's try to explicitly write out what our algorithm is going to be here. So we'll start off by saying, start with carry equals 0. You'll notice at the first digit here, the carry is always 0. And then we'll say, add each pair of digits with the carry to get a partial result. If the partial result is greater than 9, store the first digit and carry the rest. And we'll say continue until no digits remain and the carry is 0. So that's going to be our basic addition algorithm that we're going to implement. One thing to keep in mind is that our examples here have been in our familiar base 10 decimal number system. But our big integer class, you may recall, is not implemented in base 10. It's actually base 2 to the 32nd power. And that's just because working with powers of 2 is more efficient on a computer than working with powers of 10. Also, the larger our base, the more efficient our implementation. And so that's why we went with 2 to the 32nd power as our base. So what does that mean for our implementation? In particular, it's going to affect how we implement this step number 3 here when we're splitting our partial result into the first digit and the second digit. Instead of checking to see whether it's greater than 9, we're going to be checking whether it's greater than or equal to 2 to the 32nd power. So just keep that in mind as we write some code. So let's open up our big integer class. And I don't believe I've explicitly mentioned this, but we will want both addition by a small integer and addition by another big integer, as I showed in our 2 examples. And so we'll say add, and this is just adding a small integer to our big integer, and then we'll say add const big int reference n. So adding another big integer to our big integer. Okay, so let's write the implementation now. And we'll just stick that right after our multiply implementation here. Okay, so we're going to need an accumulator. So if you watch the other 2 videos that I did on big integers, or if you just take a look up here at these the implementations for division and multiplication, you'll see that we have this accumulator variable, and that basically is just holding our partial result. You'll see that it's a 64-bit integer rather than a 32-bit integer, so that we can hold 2 different digits at the same time. Okay, so let's say while n. So in this case, we're not going to have a separate carry variable. We're just going to use our starting variable here. N is going to hold our carry. So we'll say while n. Let's see, we will need an index. So we'll say I. Say I equals 0. Say accumulator equals uint64t read cell, and we're going to read cell I and add n. So that's going to be our accumulator, and then we'll say write cell I accumulator and. So this is just the equivalent of taking our accumulator mod 2 to the 32nd power. This is basically extracting that that first digit and writing that into the cell I. Okay, so then we'll say n is equal to accumulator shift right 32. So that's just, again, I mentioned n is going to act as our carry, and so we're just shifting those 2 digits over so that we have the second digit is now in our carry variable. Okay, and we'll just continue until our carry is 0, and then we're done. So now let's implement our addition of our big integer by another big integer. So similarly, we will need an index and an accumulator. And let's say const uint32t size is going to be equal to, let's get the max of cells.size and n.cells.size. So that is, as long as there's still digits in at least one of the two big integers, we're going to continue looping. Okay. And so let's say for I equals 0, and we'll say I is less than size, or here we will need a carry. So let's say uint32t carry equals 0. So I is less than size, or carry is non-zero. Increment our index. Okay, and then we'll say accumulator is equal to uint. So I think I covered this in one of the previous videos, but the reason I'm explicitly casting to uint64t here is to avoid overflow. If I were to just, for example, up here, add these two without the cast, there's a potential that that would overflow a 32-bit integer, and then we would get the wrong answer. And so we need to be sure to cast to a 64-bit integer on at least one of the operands to make sure that the whole operation is done as a 64-bit integer rather than a 32-bit integer. So we'll say read cell I plus n dot read cell I plus carry. Okay, and then we'll do something similar as we did above. We'll say write cell I accumulator and like so. And we'll say carry equals accumulator shift right 32. Okay, and I think that should be good. All right, so now rather than just call it done at that point, we really want to be able to test to make sure that our big integer class is working as intended. And we do have, if we jump over here, this big int test that we wrote, but it's basically just a copy of, I think it's problem number 16, one of the earlier problems, and that we use to exercise our multiplication and division. But this really isn't a, a comprehensive, it's basically just a sanity check to make sure that nothing is terribly wrong in our implementation. But obviously, this doesn't even exercise our addition, and so we should really add some proper testing here. And that's going to be the remainder of this video. So it may be a little bit dry and tedious, so if that's not your thing, feel free to skip on to the next video. Otherwise, let's get into it. So let's think about the kinds of tests that we might want to write for our class here. We're going to want to exercise both our small integer addition and big integer addition. That is big int plus big int and big int plus small int. So let's just brainstorm some ideas here. So let's just say, example tests. And I'm going to write these out in decimal. Obviously, again, our big integer class is not in decimal. And so these won't be the exact values that we're going to be writing. This is more just, again, a brainstorm to see what kinds of tests we might want. And so starting with big int plus small int, we might have, simple case. So that's going to be, like 0 plus 1. Actually, let's do, before that we'll say empty case, 0 plus 1. So that is the big integer just has 0 in it. So we'll say, simple case might be 1, 1, 1, 1 plus 1. And we'll say, carry no extra digit. So that might be something like 8999 plus 1001. So this is gonna have a carry, but it's not going to add an extra digit. That is, it's not going to have a 5-digit result. Oh, excuse me. I should just be 1 there. Yeah. So that's going to be equals 1001. This equals 1112, and this equals just 1. And then we'll want carry adds extra digit, and yeah, so this is the example that I was thinking of before, is something like, this plus that is 10,000. Oh, and again, I've cannot seem to do basic addition this morning. Okay, there we go. I believe that should be correct. And so that's a decent start for testing our big int plus small int implementation. So now let's look at big int plus big int. Again, we're going to want, empty case is going to be something like 0 plus 1, 1 equals 1, 1. Simple case might be something like 1 plus 1, 1, 1, 1. Oh, and one thing I should note about this is we want to do these in both directions, or both ways. That is, we expect these to be reversible. That is, 0 plus 11 should be 11, and 11 plus 0 should be 11. And so we want to do these tests both ways. You'll notice that these are not symmetric because we're adding a big integer and a small integer, and so we're only going to be testing it in one direction. These we want to do both ways. Okay, so let's see. Now we're going to want something similar where we have a carry, but doesn't add an extra digit. So something like 8899. Oh, excuse me. Carry no extra digit. Plus 1001 is that, and then carry adds extra digit, something like 8999 plus 1001 is going to be 10,000. Okay, so I think that's probably a good place to start. It's always sort of an art, I think, to come up with these test cases, because you can't test every possible input and output, especially not for a big integer class where it can hold arbitrarily large integers. And so you want to cover sort of the main use cases for your code, and so I think this is a reasonable approach. Okay, so before we can actually write these tests, there's a little bit of functionality that we're missing from our big integer class that we're going to need. Currently, we have no way of assigning arbitrary values to our big integer. You'll see we can initialize it to a small integer, but we can't initialize it to an arbitrary value. And so just for testing purposes, we're going to add another constructor here. And so we're going to say std initializer list vals. So so this here is kind of a special type. Often you'll see syntax, something like, std vector int, my vector equals 1, 2, 3, 4, 5. And so this here is an initializer list. And there's a constructor for the vector that takes an initializer list. And so we're just doing something similar so that we can use this convenient notation. So let's implement that. Also, we're going to need to compare two big integers to see if we actually got our expected result. And so we're going to need a comparison operator. So we'll say bool operator equals const big int reference n const. And so that will just compare two big integers and see if they are identical. All right, so let's implement these. Let's see. Okay, so as I mentioned, I believe I need to specify the type here. So as I mentioned, the vector class can take an initializer list to its constructor, and so we can just let me just do this here. All right. So we can do cells, vals like that. Now we have to be careful because we have this this variable num0 cells to track the number of cells that have the value 0, and so we need to initialize that. So we'll say maybe 4, or we'll say num0 cells equals 0 for uint 32t n in cells. If n equals 0, plus num0 cells. Okay, so that will allow us to initialize our big integer class to an arbitrary value. Now we need our comparison operator here. One quirk of our implementation that you should be aware of is that just because two big integers have a different size for their cells doesn't mean that they are not equal. That is, you can have an arbitrary number of leading zeros on our big integer and it doesn't change the value. And so we do actually need to iterate over cells and make sure everything matches. And so we're going to say Uint32ti for I equals 0, and then we'll say I is less than cells.size, or I is less than n.cells.size plus I. And we'll say if read cell I is not equal to n.read cell I, return false. Otherwise, return true. Okay, so I think that probably gives us enough that we can start writing our tests. So let's go back to our big int test. Okay, so all right, so we're going to want to have some code to handle just a single test case that will take, the operands and the expected value as arguments. And so we might say small addition single, or single test. And so that's going to take a big int n and a Uint32t n and a big int expected. And we'll just say n.add lowercase n, and then we'll say if not n equals expected, failure, addition of small integer had unexpected value, has. Excuse me. And then we'll say return false. Okay. And then we'll say we need something similar for adding or doing our big integer plus big integer test cases. So we'll say big addition single test, and that's going to be adding a big int n with a big int m and checking against big int expected. So we'll say n.add m, and then the rest of this is going to be pretty similar. Now, normally when we have a failure in one of our tests, we like to print out the operands and the expected value, but we don't have that functionality yet for our big integer class, and so this will have to suffice. Okay. Now, as I said, when we're doing our addition between two big integers, we want to do those test cases both directions. And so let's write some code to handle that automatically. So we'll just say bool big addition both ways, and we'll say std initializer list uint32t init n init m and big int expected. And so then we'll just say if big addition single test init n init m expected, excuse me, if not that, or not big addition single test init m init n expected. You'll note we don't have to print any error message here because we'll already have printed whichever one of these failed. We'll have printed something out. So then we can just say return false. Oh, I see. So I'm playing a little bit fast and loose with the way these arguments are passed. Like perhaps I should make these, references or whatever. It's a bit tricky because initializer lists are temporary objects, and so you can very quickly get into having to use R-value references and things like that. And so I'm just keeping it simple here. We're just going to pass everything by value. It's fine. These aren't that big. It's fine. Okay, so now we can actually write our tests. So let's say test small addition. And so let's go back to our, excuse me, up here at the top. In fact, what I'm going to do is we're going to go over here and I'm just going to keep that open, the same file open in two different panes here so that we can see our list of test cases. Okay, so for small addition, we want to do, so we're going to say, if not, what do we name this? Big addition single test. Big addition single, oh, no, that's not what we, excuse me, small addition single test. Okay, small addition single test, and our arguments are going to be an empty big int, 1, and a big integer with just a 1. Okay. Return false. At the end here, if everything succeeds, we will return true. Okay, so then we say if not small addition single test, and our next one is going to be adding 4 ones and a 1. So we'll just say 1, 1, 1, 1, and a 1. Now we have to be careful about the order here because the first element of the array corresponds to the first digit of our big integer, which is actually the rightmost digit. And so even though it's 1, 1, 1, 2, over here we're looking at this test case here. We actually need to say 2, 1, 1, 1. So the order in our initializer list here is going to be reversed. And so you can see now why I set things up the way I did. This is a very convenient, or it's very convenient to be able to notate our tests in this way. So if not a small addition single test, now we'll want to add 8999 or 8999 and 1. And so we'll say, again, recalling that we need it to be in backwards order, so it's going to be 9998 and 1. And the result is going to be 00009. One mistake that I'm already making here is that our 9 is not actually 9. It needs to be our base minus 1. And so let's actually do this. Up at the top here, I'm going to say const uint32t 9 equals, and this is going to be a little bit of a hack, but you're just going to have to bear with me here. So this is 2 to the 32nd minus 1. So this is the 9 of our base. It's not actually 9, but this is just to make our tests match up with our our decimal version of the test over here. So now we can say 9 minus 1. Put this down here. And 9. Okay, and if small addition single test, now we're going to have 9999 plus 1 needs to be 10,000. So that's just 9999 and 1 is going to be 00001. Okay, so that should be it for our small addition tests. So we'll say bool test big addition. And we'll say, what did I name this again? Big addition both ways, that's right. If not big addition both ways. And so again, we're going to look at our examples and just basically copy these into our source. So we're going to start with an empty big int plus a 1 1, and that should give us 1 1. If not big addition both ways, 1 and 1 1 1 1 1 1 1 1. Oh, I didn't actually write the result there. That should be 1 1 1 2. Again, the order needs to be reversed in our initializer list. Okay, so now we have 9 minus 1, 9 minus 1. And we're adding 1, 0, 0, 1. And the expected result is 0, 0, 9, 9. And if not big addition both ways. One last test. We have 9, 9, 9, 9 minus 1. And 1, 0, 0, 1 should be 0, 0, 0, 0, 1. All right, so now we just need to call test small addition and test big addition down here. Let's see here. So, if not test small addition, go to end. If not test big addition, go to end. End. And then here we'll say printf success. So the reason that I'm using this style, this is just a common way that I'll set up our tests where, for each test, if it fails, jump to the end, which may do some memory management, cleaning things up, something like that. But the main thing is that it jumps over this printf declaring success. So if we hit any failure, then we'll have printed failure at some point previously. We don't want to just silently succeed, so we want to be sure that we hit this printf success here at the end. Also, let's make this into a proper test. So we'll say, if sum is not equal to something, go to end. And to find out that something, let's go back. I believe this was problem, 16. So that was 1,366. And here, actually, we do need to say problem number 16 test failed. Ideally, we would write more comprehensive tests for our multiply and division, but this will have to do for now since that's not the focus of this video. Okay, let's see how things are looking. Pop back over to the shell here. Looks like we have quite a few failures. I just made a minor typo here. This needs to be cells plural. Did not make this part of our class. Let's see. Bool operator must take exactly two. Oh, that's just because I didn't make it a member of the class. Okay, and then yeah, I think that might be enough to clean it up. Let's try again. Nope. We have some additional failures. Let's just separate that. Ah, I see. I apparently did not previously make this const. It should be. Okay, so now that has built. Let's go over to our tests. Okay, so it looks like we have some failure, and so let's. Oh, we also have a typo in our. Let me just clean that up real quick. Okay. All right, so I expect that we're going to need to break out the debugger for this one. And so let me just go in here and add some debug information. Oh, we'll need to rebuild this. Hopefully this turns out to be something simple that isn't too difficult to fix. Okay, so what we're going to want to do is, let's see, was it a small or big? Addition of small integers is the problem. Okay, so let's put a breakpoint here. So that's going to be big int test 27. Okay, so it looks like we're at this test here. So let me just make sure that I've copied this test case correctly. So this should be the third one. It should be 9998 plus 1 is 0009. So that looks, I believe I've copied that correctly. Yes. So now let's go back to GDB and start over and put a breakpoint on big int test 67. Actually, before I go through this, we already have an idea of what might be going wrong because we know the test case that's failing. And so let's just take a quick look at our code and see if anything obvious pops out. So that's going to be this case here. So we'll say while n accumulator, we're going to read. Oh, obviously. That would be helpful. Okay, so it's printing nothing. That's curious. That kind of suggests that we're succeeding, but somehow skipping over. We're either hitting a failure and not printing failure, or we're skipping over the okay. So we did not return true at the end of this. Okay, great. We have success. So thank you for sticking with me through this video. It was a little bit longer than my typical video, but we got to see the implementation of big integer addition, and then also writing some really comprehensive tests for that code. And so now we can have some confidence that that code is correct going forward. Also got to see a little bit of a debugging technique that was not originally planned, but I'm glad that that wasn't too difficult to resolve. In the next video, we'll be using this code to solve the next Project Euler problem, as I indicated. And then that problem, I believe it was problem number 25, can also be solved using analysis. So it was problem number 25. And so in the next video after that, I'll be solving it with analysis alone. And so please look forward to those videos.